Sigma notation. We're going to be taking a lot of sums, and so it helps to be able to express sums in a compact manner. And sigma notation utilizes this capital Greek letter sigma in order to express sums. For example, we have this sum over here. Okay. Now, what's to the right of this sigma is called the sum end, and what we're summing through is called the index. So this has a lower limit of 1 and an upper limit of 99, and we're summing this expression. What does that mean? Well, as we go from k equals 1 to 99, we add k, depending on which k we're at as we're increasing. So for the first one, k equals 1, we get 1. For the second one, k equals 2, we add up 2 to it. So we could continue doing this all the way up to the upper limit of 99 to get that this whole sum, now expressed in a very compact manner, is equal to 4950. Here are some other sums. What does this mean? Well, the sum end here is 1. Okay? So as we go from k equals 91 to 99, we just get 1s on each of these, and we get a 1 99 times. And so that equals 99 there. We could also have an upper limit as some other, as some symbol. Okay, here we're using n, and we treat the symbol as fixed, although we're summing to it. So here we have k equals 1 to this arbitrary now, n, which we think about as being fixed, and we sum all the way up to n. We could also have a different index than k, so here we have the index of I, and notice the lower limit here is 0 rather than 1, as it was in all the other examples, and we're summing that up to 3. So what does that mean? Well, our sum end is I squared, so we start at I equals 0, 0 squared, plus the next value of I, which is 1. And what do we do with that 1? Well, we look at the sum end to see what we're doing with that 1, and we're squaring it. So we add 1 squared. That's the next. Then we go to I equals 2. And what's the sum end? I squared, so we're going to take that 2 and square it. Take this, next is 3, and then square it. And we're only summing up to 3. And so we get that this sum is equal to 14. We could even have negative lower limits of the sum, or lower bounds of the sum, sometimes you'll hear. And this sum end now is k squared plus k. And so for each k from minus 1 to 2, we plug in that k into the sum end and then go to the next value. So this one was for minus 1. The next value is going to be 0, 1, and we stop at the upper limit of 2, and this will equal 8. Now here are some rules that we could use to help us evaluate sums. One is the constant multiple rule. So if you have this expression here, the of k, okay, so you could think about this a sub k as some function of k. So for example, here it would be k squared plus k. If we have an expression of k with some constant multiple, well, we could pull out that constant, okay? So for any real number, this would work. You could just factor out the c. We also have the addition rule. So here we have the sum of these two now expressions of k, or functions of k. And we could then, if you will, distribute that sigma to each of these. So the sum of the expressions ak plus bk is equal to the sum of ak plus the sum of bk. So in other words, taking a look at this example above, what we could have done is say, well, that's just equal to the sum from the bounds that we have of k squared plus the sum k. So we could have broken that up into two different sums. Okay, and of course you're starting at k equals -1 to 2 and k equals -1 to 2. Okay, and finally we have sums of powers of integers here. This is just to deal with common sums. Okay, so one common sum is to just have a constant in there, like we saw above. Here we just had the constant 1. Well, that's just going to equal c times n there. Okay. We also, another common sum is to just have k, and here we have this formula when we're summing up to an upper limit of n. And likewise, we're summing here from k equals 1 to n of k squared, and we get this expression. And for k cubed, we get this expression when we're summing up to n. We'll make use of some of these formulas for future calculations.